Okay, continuing on today with the series playlist, I want to find the power series for natural log of 1 plus x. And for this, what I want to use is we have the geometric series formula over here to the right. The similar part is it's close. We've got 1 minus x here and we've got 1 plus x here. So in order to do something similar to this, we can kind of just rearrange this. One thing to notice is we're going to need for the convergence, we're going to need the condition that the absolute value of x is less than 1. So in order to use this, what I'm going to do is something really similar. For instead of using 1 minus x, let's create something like 1 minus minus x. So all we've done is put something exactly in this form, but this here in the denominator is actually 1 plus x. And then using this formula here, what this is going to be, we just actually plug this in as the input into this. So we have, this is going to be sum from n equals 0 to infinity of minus x to the n. And so let's just rewrite it a little different. We'll have this is the same thing as 1 over 1 plus x. And then here, for the minus x, I can split this out and write it as minus 1 to the n, just distributing in the exponent times x to the n here. And then from here, what I can do is I just want to differentiate, I want to integrate on both sides. And the reason for doing that, so we're integrating with respect to x. The reason for this is on the left side, when we integrate this, this is just going to be our goal, which is natural log 1 plus x. So to get our value for this, we just need to work with the right side. The thing I want to do first is I want to swap the order. I want to swap the integration with the sum. I can do this here because we've established, we're assuming absolute convergence because we're assuming we need our x value to be because we're assuming we need the absolute value of x to be less than 1. So this is going to allow me to do this swap. And then when we do this, the minus 1 over n, this is just a constant. So we're just doing power rule on this. So I can actually bring this in front of the integral so we don't have to even worry about it. So we could have minus 1 over n in front. Then power rule on this is going to be x to the n plus 1 over n plus 1. And one thing I'm forgetting is a plus c. You could put it, usually it's kind of nice to put it in front, but let's do it like this. We'll put our plus c right here that we can figure out in a second. Actually, I think I want to figure out the plus c right now. So what we can do on this is we just need to find some nice value to plug in. If we use 0 here, this is going to help us figure it out. So let's just plug in 0 on the left. That's going to be natural log of 1. And then on the right side, you plug 0 in here. Every term is 0. So this whole piece is 0 plus c. But natural log of 1, that's just 0 as well. So that tells me that our c value needs to be equal to 0. So if c is 0, let's just get rid of that from our problem, get rid of all this junk. And then one more thing I like to do on this, let's do an index change. I'm going to, just to kind of get rid of these plus 1s, I can subtract 1 on both these, and then so I don't change it, I just need to add 1 here on the index. So we'll add 1 here. And so this stuff is going to cancel out right here. And so for our power series, natural log 1 plus x, we're going to have just the sum from n equals 1 to infinity minus 1 to the n, x to the n over n. Now, one thing we can do before we finish up, going back to the convergence, we established this earlier, but this is not necessarily exactly the case for what we have here. After you differentiate or integrate a series, you need to check the endpoints again. So we need to check the values at x equal to minus 1 and 1. We know the radius of convergence stays the same, so we're basically going to have this kind of setup, but we're just trying to find out if this 1 value or in this minus 1 value is going to be okay. So what we can do is just come down here. So what we can do is just come down here and plug in each of them. So first, let's start with x equals 1 and plug in. So this is going to become, so this will just become our sum. We'll have minus 1 to the n. Plugging a 1 in for x, we just have 1 over n here. But this is basically our alternating harmonic series. And we know this to converge. So this is going to be fine for our x equals 1 value, and we can include that. We'd say x can be greater than or equal to 1. And then next, same kind of thing, we just want to check when x equals minus 1, the other endpoint. So then when we do that, what's going to happen? We have minus 1 to the n. Here we have this actually, we plug in minus 1, this becomes another minus 1 to the n over n. And then let's put together these values in the numerator. So multiplying that together, adding exponents, because we get the same value, this becomes minus 1 to the 2n over n. But now 2n is always even. Minus 1 to an even power, that's going to be just 1. Now we have the harmonic series, 1 over n. this one actually diverges, and it's a common value, so you may just remember it, but also if you did p-series on it, an exponent of 1 or less means this is going to diverge, so we're just going to leave off that endpoint -1. And so if we want, we can take this and write our convergent this way. We can write this as -1 to 1, but on the right side, we can have the square bracket showing we're including 1, and here we have the rounded bracket saying that we're not including the -1. Okay, that's it for today. Thanks everyone for watching. Have a good day.